Fantastic. So pulling this all together, we're going to be using the Chatbot application, which runs on Kubernetes, using the method that Simi described to demonstrate the self-healing power of Kubernetes. So first, we will SSH into the master node. There are 3 nodes in this K3's cluster. We can use kubectl to see the nodes that are running in the cluster. Kubectl is a command line utility to interact with the Kubernetes API. You can see there's 3 nodes there. They're all running already. That's great. We can also use kubectl to see all the pods that are currently running on all the nodes. So we can do that by doing kubectl get pods, and then we have to specify all namespaces because they're categorized in those namespaces. All right, you can see here on the left that there's a bunch that belong to the Chatbot application. And we can see on the left here that the Chatbot application is in night mode. We're going to just show how we can actually interact with it. We can post hello world, for example. It's a messaging application as Scott described. And we can also post to it with chatbots. And this is what we're going to be doing now. Each chatbot is going to post intermittently to the Chatbot application so we can see which pods are up and running and which pods are down. So let's just cd into the chatbot directory. You can see there's some really important files here. We're going to take a look at chatbot-deployments.yaml and main.go. So the YAML file is what defines the desired state of the Kubernetes cluster. So let's check that out right now. We can see on the very top, it creates a new namespace, just like we had Chatbot application namespace. Now we have Chatbot. It also creates 3 deployments. And all the deployments are very similar to each other. The thing that really differentiates them is this preset right here. The preset is a flag that's passed into the base image, which I will show you right now with main.go. So main.go is the actual program that posts to the Chatbot application. And it has a number of presets. Each preset for the interns has a username, a list of messages it's going to be posting to the Chatbot application, and an interval for like 3, 4, 5 seconds. And to apply this to be our desired state, we can do kubectl apply f for file, and then using that file, we can create the chatbots. You can see 3 deployments were created. We'll go back to that later. On the left here, you're going to start populating the Chatbot application. All right, that's beautiful. So what happens here? We have 3 chatbots at the very bottom. We can see they're all in the chatbot namespace. That's perfect. Pod can go down for many reasons. For example, another process could be running alongside a container in the same C group, just as Sabine was talking about, where the CPU was kind of overtaken. And we're just going to be simulating this by doing a manual deletion of a pod. So if you take a look at the Sabine pod, which is the 3rd to the bottom, it has a randomly generated name that ends with dfgpx. So what happens when we delete that manually? We can delete it by doing kubectl and then delete, specifying that it's a pod we want to delete, popping that name over. We always want to make sure we also specify the namespace that the pod can be found in. So we'll do n chatbot. All right, on the left, you can see nothing's posting, so Jose, Josiah, and then, all right, Sabine's back up already. Let's see what happened there. We just do kubectl get pods again. All right, Sabine bot is there. It's at the very bottom now instead of the 3rd to the bottom. And we can see the end dfs8s is different than it was before, which means that it's a new pod created with the same specifications as the old pod. So what happened here is, just as Theo was describing, the desired state was compared to the actual state. And the actual state only had 2 pods, while the desired state had 3, and so it spun up a new pod in its place. And it took almost no time, so it was almost not even noticeable. All right, beautiful. As a side note, we can actually look at the deployments here. And these are our desired states. We can have 3 deployments, Josiah, Jose, and Sabine bot. What happens if we delete a deployment? Well, if we delete a deployment, then it's actually changing the desired state of the Kubernetes cluster. So in the desired state, now there's only going to be 2 pods, while in the actual state, there'll be 3. And so the actual state will be manipulated by the controller to fit the desired state and only have 2 nodes. Only Jose and Josiah are posting now. That's exactly what we want. That's perfect. All right, now moving into phase 2 that Sabine described, we're going to be working with node failure. So node failure can also happen for a number of reasons. A reason that I think Sabine described was one pod might fail and bring the whole node down with it. I'm just reapplying the chatbots right now. So they're going to be all up and running again, and we can see what happens when a node fails. So let's first talk about which node these are running on. All the bots are running on the same node right now. And we can actually see that in just a second by looking at the IP addresses of the nodes they're running on. And we're going to simulate a node failure by just doing kubectl delete or kubectl drain, which is going to evict all the pods from that node and simulate a node failure. First, let's look at these pods. All right, so we can use the same command we used last time, but just add O wide, and we can see a lot more information. So at the very bottom, chatbots, you can see the node they're running on, IP 172.319.145. So this is the IP address or the DNS of worker 1. They're all on the same node because we actually tainted the second node to make it so pods prefer not to go on that node. And when this node fails, we'll see how Kubernetes reacts. So we're going to do kubectl drain, specify the node we want to drain, and then just add some very convenient commands at the end to clean things up. And let's see what happens on the left here. So everyone's posting right now. And once we do drain, it's going to evict all those. Posting stops for just a second. And now it's up again. Perfect. All right, let's see what happened there. So remember before it was running on worker 1, which is 172, it ends with 145. And now they have different randomized names, and they're also running on worker 2, which ends with 32. So what Kubernetes did, just as it did with the pods, is it was always comparing the desired state with the actual state, and it saw that the actual state had a node failure, all the pods were deleted, and so it fixed everything and just moved it on to the other pod that was not preferred, but actually worked. All right, so this all demonstrates the self-healing power and the resilience of Kubernetes, and I will pass it on.